Hello, Dan, the biology tutor again. Um, just before I start, this short video will be on the topic cell physiology. Just before I start, my details are on the screen there, my mobile number, and I do tuition in all of those areas there. My normal way of working is you get in touch with me if you want to do a particular topic. Get in touch with me by text. And tell me what topic you want to do, whether it's a GCSE biology, GCSE physics, AS biology, A2 biology, whatever topic. I will then post to you a complete package of notes and question booklets and so on, so that you get the best benefit from the tuition. So, for example, in this topic that I'm going to look at today, cell physiology, I would have posted you a set of notes which covers the topic perfectly and is very precise. And the notes you'll find they will definitely help your understanding way beyond what you maybe have now. So you get a set of notes, a great set of notes. You'll also get a set of questions, which are questions that are handpicked to cover the topic perfectly and to do with the most relevant parts of the topic. You'll also get answers to those questions, answer scheme for all those questions. You'll also there's also supplementary materials here. These are what I sometimes refer to as short questions. They're not actually that short. They're actually very searching. Some of them are much the same as normal exam questions, but they're designed. There's some in this particular topic, for example, there are 67 questions here to try and cover the whole topic, and they're designed to allow you to see the depth of the questions that you can be asked, and also to give you some confidence that once you've the topic completed, you go through these questions and you can answer them all, then you're doing fine. And there's a set of answers for these questions. So that's the complete package. You get in touch with me by text, and I'll post that to you, and you'll have it the next day. And then once you have it, then we can do we can do a Skype session if you want, or you can watch the video here on this topic. Now you'll find the video. This video isn't of much use to you unless you have these notes and questions, because I'll be making a constant reference to the notes. And for example, rather than drawing diagrams on the screen here, which takes forever, and I simply wouldn't be able to cover the topic in even an hour. Rather than doing that, everything's in the notes. The diagrams are done perfectly in the notes. So if you have the notes in front of you, then you have the same notes as I have here, and so you can refer to them as you go through the video. And you'll see me referring to the notes frequently. That's not because I don't remember what the material is, but it's so that I always constantly referring to it, make sure I don't leave anything out. So all the points are essential. There's no excess in the notes, and everything should be in here to cover the AS specification. So there you are. In a previous video, I did a session on osmosis, and that's the water potential, solute potential part of this topic. What I'm going to do here is the other half of it, which is sometimes done first by teachers and sometimes done after the water potential. And today's video is going to deal with diffusion, facilitated diffusion, active transport, and endocytosis and exocytosis. So these are all mechanisms by which molecules get in and out of cells, by which molecules and ions and other substances can travel across the cell membrane to get in and out of cells. And you'll see on the first page of the notes there, I sort of list a few things that a few molecules that might be moving in and out of cells. So things like water, ions, glucose, carbon dioxide, oxygen, etc. Those are all things that the cell might need. So for example, the cell might need oxygen for respiration. It may be releasing carbon dioxide from respiration, it may be taking in particular ions that it needs for some production, for example, taking in nitrogen ions or sulfate ions or some other atom is taken into the cell. Carbon dioxide, as I said, to produce during respiration. Now, there are various ways then in which, various mechanisms by which molecules can get in and out. Molecules, when I say molecules here, I'm including ions, atoms. Ions you might refer to as minerals sometimes. Biology refers to them as minerals, but they're actually properly called ions. So, for example, magnesium ions or calcium ions or sulfate ions and all these things. You've come across these possibly in the molecules topic already. You're aware that cells and tissues and so on require calcium ions for certain things, and magnesium ions and potassium ions and sodium ions and so on. So that's what we're looking at here. So I've said here some molecules can pass through the cell membrane by passing through between the phospholipids. So you need to have done the structure of the cell membrane at this stage. You need to know what the structure of the cell membrane. If you haven't done the cell membrane and the cell topic, you'll see that I've done it sufficiently here, hopefully for you to understand it, and you'll come across diagrams of the cell membrane that I've put into the notes here, and to help explain what we're talking about. So we're talking about substance getting across the cell membrane. So from the cell membrane, then you're aware that the cell membrane is essentially made up of what are called phospholipids, 2 layers of phospholipids. And the 2 layers of phospholipids are arranged in the cell membrane. You get a phospholipid like that, you know, a phospholipid like that. And the 2 layers of phospholipids are arranged so that they're heads as well. So if that's the cell membrane, the phospholipids are arranged like that. If you've got heads of the phospholipids facing out and the heads of the phospholipids facing in, and the tails, as it were, of the phospholipids then, as it were, touching together, tails or legs, whatever you want to call it. So that's the structure of the cell membrane. So it's mostly made up of phospholipids. Now, something you learned about these phospholipids is the heads are hydrophilic and the tails are hydrophobic. So the heads are quite happy to be close to water. They're attracted to water. They're okay to be in water. Whereas the tails are hydrophobic. The tails don't want to be anywhere near water at all. They're repelled from water. And a question that's often asked, and maybe in a different part of the course, would be why do you have 2 layers of phospholipids, and why do they arrange like this, 2 layers like this with their tails together, as it were? And the answer is that and here you have the cytoplasm. Cytoplasm is mostly water, okay? And outside the cell is mostly water and the so-called tissue fluid. So you've got water outside and water inside. So the best arrangement is you have the heads of the phospholipids touching the water, so they're quite happy because they're hydrophilic, and the heads out here are touching water, and the tails are kept away from the water. So these two layers of these tails, 2 layers of tails are kept away from the water. Imagine if the cell membrane was just 1 layer of phospholipids. Then the heads would be okay because they've been in contact with the water inside, but the tails then have been in contact with water outside, and that wouldn't work. They'd be repelled from water. So this is a good arrangement. 2 layers of phospholipids arranged like this. So you often get that question then. Explain that arrangement. So you have to talk about the hydrophilic and hydrophobic aspect of the phospholipids. By the way, I don't apologize for going fast here. I need to talk very fast and go quite fast if we're going to get the topic covered in even an hour. So that's why I'm going fast, and hopefully you can keep up with me. You will be able to keep up with me if you have the notes, because in the notes, essentially, I'm working from the notes and I'm covering all the areas, and everything I say here should be covered in the notes. Possibly some things I explain like this maybe isn't covered in this set of notes, but if you get notes maybe on molecules or cell, then that would be explained somewhere. That would be explained, if I remember correctly, that's explained in the cell topic. Not okay. So different schools would do it slightly different ways. Sometimes some things would be explained within one topic and not in that topic. So important thing to know is that the tails of the phospholipids are hydrophobic. And they repel water. So you'll see that the tails, and I've underlined this very clearly in the notes, the tails of the phospholipid molecules are hydrophobic. And hydrophobic, they allow what are called non-polar molecules, or hydrophobic molecules, to cross the membrane. So they allow molecules like themselves, like oils, to cross across the membrane, and what are called non-polar molecules. Now the word polar is used here, and you haven't come across that word polar before. Non-polar means that the molecule doesn't have plus and minus charges. It's not an ion. It's not an ionized particle or an ionized molecule. So non-polar simply means that the molecule is not charged. And in contrast, then the word polar is used in biology to talk about things that are charged, that have charges. So, so the obvious things that are polar molecules or polar substances are ions. So you have magnesium ions and calcium ions, they're all positively charged, and you have chloride ions, they're negatively charged, and so on. So this is the difficult part of this idea of polar and non-polar molecules. And I've said there, because polar molecules, or sorry, non-polar molecules can get across, are quite happy to be in contact with these phospholipids, then polar molecules can get across the membrane quite easily. Or sorry, non-polar molecules can get across the membrane quite easily. However, charged or polar molecules, when they come in contact with these phospholipid tails, they can't get through. And they simply can't get through. They're repelled by these hydrophobic tails. So I've said the tails of the phospholipid molecules are hydrophobic. They allow the passage of hydrophobic or non-polar molecules to get through. However, the phospholipid tails, however, act as a barrier to any hydrophilic or polar or charged molecule, or anything that's water soluble as well. So ions, polar and water soluble things can't actually get through the tails, past the tails of the phospholipid molecules. And it turns out then there needs to be a sort of a special arrangement made to get ions and polar molecules and hydrophilic molecules through the cell membrane. But we'll come to that in a wee second or two. Now, the first thing to say is that carbon dioxide and oxygen are two things that are moving in and out across the cell membrane. And they're non-polar substances. So they actually can pass quite easily through between the phospholipids, past the phospholipid tails. They can easily pass through between the phospholipid molecules. Water molecules are a special example too. Water molecules, even though they are polar, they get a kind of a bye here. They can get through because they're extremely small. And water molecules can actually can get through, pass through in between the phospholipids. And they're so small they can slip through between the phospholipids. Okay, now we'll come back to all that detail as we go along here. Water molecules are small, then can pass through between the phospholipids. Okay, so each of those different situations I'll elaborate on here gradually as we go along. So we're now going to talk about 4 different mechanisms or methods by which substances can cross across the cell membrane. And the 4 mechanisms are simple diffusion, facilitated diffusion, active transport, and cytosis. Cytosis includes endocytosis and exocytosis. And you came across it a bit at GCSE, you came across something called phagocytosis, so that's the same thing. So we're going to start first of all with simple diffusion. And simple diffusion is simply the movement of a substance across the cell membrane from a high concentration to a low concentration through the phospholipid, so-called phospholipid bilayer, between the phospholipid molecules. The movement of substances from where they're at a higher concentration to a lower concentration, and it happens through between the phospholipids. In other words, molecules simply leak through the cell membrane by going through in between the phospholipids. And looking at the notes there, you'll see simple diffusion happens when molecules pass through between the phospholipids. Examples of things that do this are water, oxygen, and carbon dioxide. They can easily diffuse across the membrane in this fashion. And you'll see from the diagram there that each of those 3 molecules can pass through, simply slide through between the phospholipids. And simple diffusion then happens from a high concentration to a low concentration. So if you had a high level of oxygen outside the cell and a low level of oxygen inside the cell, then the oxygen molecules could slide through between the phospholipid molecules. They're very small and they can slip through. Why would you have a low level of oxygen inside the cell? Well, if the cell is using up oxygen for respiration, then the level of oxygen inside the cell will remain low, and therefore oxygen then will simply diffuse across the membrane. So simple diffusion, you see there, simply involves the phospholipid molecules and molecules slipping through between them from high concentration to low concentration. I've said there, simple diffusion is passive. That's a term you maybe come across at GCS, maybe not. Passive simply means there's no energy involved. The cell doesn't have to do anything. Cell doesn't get involved. There's no energy needs to be produced. There's no need for ATP or anything. It's this process simply happens if you've got a high concentration of oxygens outside and a low concentration inside. They'll simply move across the membrane to even up the concentration. No energy required. Now, a question that's often asked is, in what sense is simple diffusion a selective process? Selective. And you'll see in questions to do with this topic that word selective comes up quite a lot. Why is this process selective? Basically what it means is, why is simple diffusion, why does it essentially only let certain molecules through? And the answer is, to get through by simple diffusion, you have to be small enough to slip between the phospholipids. Okay, you have to be small enough, and you also have to be non-polar. You shouldn't be charged. As I say, water is an exception because water is a charged molecule, but it still gets through on the basis that it's very small. So we're now going to look at what factors affect the rate of diffusion. The rate of diffusion, how quickly molecules move across the membrane by simple diffusion. And such things as the size of the molecule. So water and carbon dioxide and oxygen are quite small molecules. If the molecule is slightly bigger, then it might have more difficulty getting through. Its movement through this membrane would be slower. So the smaller the molecule, the faster it can diffuse across the membrane. Concentration gradient. Well, that concentration gradient is about the difference in concentration. So if you have a very high concentration of oxygen outside and a very low concentration of oxygen inside, that's a big difference. That's called a big concentration gradient. Then the rate at which the molecules move across the membrane is quick. Whereas if the concentration inside and outside is only slightly different, that means a small concentration gradient and the movement is much slower. So a concentration gradient is very important. High concentration gives a faster rate of diffusion. Temperature has an effect. Generally from chemistry and from physics, you know that molecules, when they have higher temperature around them, molecules are moving faster. And this process of diffusion is simply a physical process or a chemical process. It's really just the movement of molecules from high concentration to low concentration. If everything's at a higher temperature, then the molecules are moving around faster. They've got more kinetic energy, and so they can diffuse faster. So higher temperatures gives a faster rate of diffusion. The amount of surface area of the membrane is important. So in this particular case, that's the surface area. That's the surface of the membrane there. But imagine if instead of the membrane looking at the membrane was folded. So instead of looking at the membrane was folded like that. Well, now you've got much more surface. You've got all this surface here. And so you've got more surface across which the molecules can diffuse. And you'll find that many cells do have an increased surface area. That we refer to as microvilli, which you find on the surface cells. You'll come across that in another topic. More surface area means the faster diffusion is. The thicker the surface. Now, diffusion doesn't happen across cell membranes. Diffusion will also happen through layers of cells. So if you had a layer of cells and then you had another layer of cells, or even if you just had a single layer of cells, an example of where you would have a single layer of cells would have been in an alveolus. So alveoli in breathing, alveolus looks a bit like that, and it's made up of, if you remember, its walls are 1 cell thick. So these drawings are not going to be that good, but basically it's 1 cell thick. So the oxygen's having to, oxygen coming in here, so the oxygen coming into the alveoli. The oxygen then is diffusing across this layer of cells into the bloodstream. The thinner this layer, the better. The shorter the distance the molecule has to diffuse. And you'll see this always in biology, the thinner the surface or the fewer the layers of cells, or the thinner the layer of cells, then the faster the molecules can cross across. So I've just said there, this is we're talking about, I keep referring to it as diffusion, but really its proper name is simple diffusion. Simple diffusion can happen across a cell membrane, it can happen across several membranes, or it can happen through a layer of cells or several layers of cells. For example, as I've said, in the alveoli. Other places where you come across diffusion would be in a later topic when you're looking at the diffusion of food molecules from the cavity of your digestive system into the cells lining your digestive system, and then further into the blood vessels where food is being absorbed in your ileum. And the ileum is part of a topic that's coming at the end of this module, which is module 1. Okay, so that's simple diffusion. Simple diffusion then simply involves phospholipid molecules, and the molecules then that are moving by simple diffusion have to, as it were, sneak through between the phospholipids. Now, the second kind of diffusion is called facilitated diffusion, and you won't have come across this at GCSE at all. And I've said this is a kind of diffusion which is facilitated or helped by the presence of so-called membrane proteins. So in this case, this diffusion can't happen in the normal way. It can't happen through between the phospholipids. It requires the presence of so-called membrane proteins, proteins that are present in the cell membrane. And if you've done the cell topic and you've looked at the cell membrane, you realize that as well as phospholipids in the cell membrane, you find that there are lots of large proteins in the cell membrane. So large proteins dotted about in the cell membrane as well. And it's these large proteins that are involved then in the movement by facilitated diffusion. And I've said here that this is needed for charged or so-called polar molecules, water-soluble molecules such as ions, and also for big molecules such as glucose. So why is it needed then? Well, first of all, if you're an ion, the so-called polar molecule, you can't get through the phospholipid layer because it's hydrophobic. It'll not let you through. So polar molecules simply can't get through here. Even if you were non-polar and you're too big, if you're a big non-polar molecule, you still can't get through because you're simply too big. So really, this is a kind of a diffusion for bigger molecules and for ions that allows them to get through the cell membrane. So this is needed for polar or charged water-soluble molecules such as ions and for big molecules such as glucose. By the way, you're probably thinking now, do you have to know and do you have to remember how a particular substance then does go across the cell membrane? Well, I've already said that oxygen and carbon dioxide in water can travel through by simple diffusion. And now I'm talking about glucose. The answer is no. You're not going to be asked a question in the exam that says, explain how glucose gets across the cell membrane. You don't have to specifically know how glucose or amino acids or some other particular molecule gets through. You essentially have to know just about the different techniques. And if you remember examples of molecules that travel or get across the membrane in this way, very good. For facilitated diffusion, I'd be remembering ions. This is how ions get through the cell membrane because ions can get through by simple diffusion. So this is for ions, and it's also for bigger molecules. And glucose is quite a big molecule compared to water. Now, these proteins then are what let these molecules get through. And there are two kinds of proteins that are involved. There are proteins called channel proteins. Now, channel proteins are what their name says. Channel proteins, and I'll just do a very rough diagram. A channel protein is simply a protein with like a channel through the middle, sort of like a space that runs through the middle. So basically a protein with a hole in it. And it sort of makes sense that a molecule then might be able to pass through this channel. And that essentially is what happens. The channel proteins are big proteins in the cell membrane that have pores through them. So they're proteins with pores. Channel proteins, these proteins have a central, what's called a hydrophilic channel, or a hydrophilic pore. And that means, because it's hydrophilic, it's very friendly, as it were, to hydrophilic molecules, such as ions and polar molecules. A hydrophilic channel which allows ions and other polar or water-soluble molecules like ions to bypass to get through. And what in fact it's doing is it's allowing these charged or polar molecules to bypass the phospholipid layer, to bypass the hydrophobic tails of the phospholipid layer. There's no way these ions can get past these hydrophobic tails. However, if they go through one of these channels, it's like a sort of a side entrance. It's a quick way for the for the ions to get in without coming in contact with the hydrophobic tails. So this hydrophilic channel allows polar and water-soluble molecules to bypass the hydrophobic barrier created by the tails of the phospholipid molecules. So it allows them to bypass that. Now, you definitely need my notes here, because most of this is in diagrams, and the diagrams are complex compared to what I'm doing on the board here. Complex diagrams. So you'll see there that I'm drawing a cell membrane, and we're looking at different types of ions that might be trying to get across the cell membrane. I've actually shown two different ions there, different shapes. And what we see is that for any particular ion or any particular molecule, there's a specific channel protein for that molecule. In other words, if you're a sodium ion and you're coming close to the cell membrane and you want to get inside the cell, you have to find a channel that fits you. You have to find a channel that allows you to fit through it to get into the cell. If you're a different ion, if you're a magnesium ion or a calcium ion, then you have to look for a different channel, as it were, different protein with a different shaped channel. So each different ion that's trying to get across the cell membrane, each different polar molecule, needs its own specific channel protein that's the right shape for it. I've said each channel protein has a specific shape. So each is selective, allowing only one shape of ion to get through, allowing only one particular ion to get through. Now, something that's also mentioned in the textbooks, and it's not too important, is that these channels can be open or closed. Sometimes they're permanently open, but sometimes they can be closed. They can be such that they can close their channel or open their channel, in which case they're called gated. They're said to be gated proteins or gated channels. That's not too important. Not too important. It doesn't come up anywhere else in the rest of the course. So essentially, facilitated diffusion can happen due to these so-called channel proteins. Proteins that have a channel down the middle. What's facilitated diffusion for? It's for polar or charged molecules such as ions. It's also for larger molecules such as glucose. Ions and glucose cannot go through by simple diffusion. They can't get through. They pass the hydrophobic tails and the phospholipid layer. So they need this special way of getting through, and they can slide through these pores, these so-called hydrophilic channels in these so-called channel proteins. But that's not the only kind of protein that's involved in facilitated diffusion. There's a second kind of protein called a carrier protein that is also involved. Oh, by the way, just before I leave the channel proteins, most water molecules, despite the fact that water molecules can slip through the phospholipid layer by simple diffusion, most water molecules actually come through channel proteins. And they have special channel proteins dedicated to water molecules, and they're called aquaporins. Aqua, water, porins, pore. Aquaporins, and you'll come across aquaporins in A2 again in the kidney. So that's something to remember. Aquaporins, specially designed channel proteins for water. And now there's a second kind of protein that's involved in facilitated diffusion, and that's a so-called carrier protein or protein carrier. Some textbooks say protein carrier, carrier protein. Once again, it's a big protein that's in the cell membrane. So I'm going to pop a big protein just here in the cell membrane. So this may be a carrier protein. And now, how is it different from a channel protein? I'm sorry, my channel protein is not well drawn there. I just draw the channel protein a little bit better. So this is a channel protein with its channel, and this is a carrier protein. How's a carrier protein different from a channel protein? Well, first of all, the channel protein's got a channel through it, and that channel is usually open. It's usually open, as I said. Sometimes they can be open or closed, but usually it's open. Now, carrier proteins, they don't have any channels. But what they'll have is they'll have a place on the surface. And on the outer surface, they'll have a place where, a bit like an active site in an enzyme, they'll have a place on the outer surface where molecules can attach to them. So molecules can fit into them or attach to them. So for example, this carrier protein has a place on the surface, and this particular molecule here, this particular ion may attach there to that place. A bit like an active site. So the ion can attach into it. And now notice there's no channel. But here's what happens. Once the ion or the molecule attaches to the carrier protein makes a channel for it, or makes a way for it to get through. So what we're saying is there's no channel to begin with. There's no door open, as it were. But once the ion attaches, the protein kind of opens up a channel and lets it in. So my way of looking at it is channel proteins are open all the time. Open channel. It's like an open door. You come here. If you fit through, you can go through. Carrier proteins, you can attach to them. If you're the right shape, you're the right molecule, you attach them, and they'll make a channel for you and let you through. And once you get through, the channel closes again, or they close up. So they're like closed doors that if you kind of fit into them like a key, then they open for you and they let you in. Carrier proteins, and I've said here, glucose and amino acids can only cross the cell membrane by binding to a site on the surface of special carrier proteins. So that molecule that's attached there to that carrier protein might be a glucose or an amino acid. You don't have to necessarily know that, but it's just that's how glucose and amino acids get through. The carrier protein is then, once the molecule binds to the surface, the carrier protein is then set to change shape, to take the molecule in across the membrane. Take shape in inverted commas. Change shape. The change in shape, you imagine it just like a channel appearing in that carrier protein. And you'll see from my diagram in the notes there, you'll see what happens. Carrier protein initially, the molecules are attaching to it there on the outside surface of the membrane. Once they attach, the channel opens and lets them through. And then once the molecules are all through, the channel closes again. So carrier proteins in this case are proteins without a channel to begin with, but they make a channel and let the molecule through. Now, once again, this is still a type of diffusion. So this will only happen from a high concentration to a low concentration. Facilitated diffusion. Truth be told, facilitated diffusion, you need to know about it at AS, but it rarely comes up on the rest of the course at A2. So it's something you need to know about now. And the other thing to say about it is it's also a selective process. Selective, what do I mean by selective? Only certain molecules can get through the cell membrane through these so-called carrier proteins. What I mean, only certain molecules? Well, you must fit into a carrier protein on the cell membrane. You have to fit. If there isn't a protein with a shape that allows you to fit into it, then you can't get across the cell membrane by this mechanism. So different molecules approaching the cell membrane might have their own carrier protein in the cell membrane for them. And so it's often said that if a cell is taking in a lot of a particular substance, like say it's taking in a lot of glucose, then you'll find there's a lot of carrier proteins for glucose in its cell membrane. If another cell is taking in a lot of some other substance, like amino acids, then you'll find there's lots of carrier proteins for amino acids. In other words, you can't just approach the cell membrane and just jump on board any carrier protein. You have to have one that's specific to you. So there's lots of specificity here, lots of selectivity here, selective. So the membrane, these are selective, then only certain molecules can get through. So if I said there, if a cell needs a lot of glucose, its cell membrane will contain large numbers of carrier proteins specific for glucose. Note once again, this facilitated diffusion doesn't need any energy. So it's just a diffusion. There's no energy involved. It just happens across the cell membrane, and it happens from a high concentration to a low concentration. So you have to have a high concentration. You have to have a lot of the molecule on the outside and less of it on the inside, or vice versa. That's quite confusing, that facilitated diffusion, because it involves two kinds of carrier proteins, channel proteins and carrier proteins. We'll come back to that in a minute or two, because in a moment or two we're going to compare all these different mechanisms. Now, the last mechanism we're going to talk about is active transport. Now, this turns out to be the most important one overall in the biology course, because next year in A2 you'll come across active transport all the time. In fact, you'll come across it later on in AS, active transport. And you remember active transport from GCSE? Active transport was the one that required energy, wasn't it? And it moved substances against the concentration gradient, in other words, from a low to a high concentration. And you come across active transport, for example, in root hair cells. Do you remember root hair cells taking up nitrate ions from the soil? The root hair cells were able to take up the nitrate ions, even if the concentration of the nitrate ions were low in the soil and high inside the cell. In other words, the cell membrane of the root hair cells was able to move the nitrate ions against the concentration gradient. And because it was against the concentration gradient, it kind of makes sense that this process required an input of energy. In other words, it's described as an active process. An active process is where the cell has to contribute something, in this case energy, in the form of ATP, which is an energy molecule. So active transport is against the concentration gradient. It will move substances across the membrane, even if the substance is moving from a low to a high concentration. Okay, so active transport moves substances across the membrane from a low to a high concentration, i.e. against the concentration gradient. Energy is required, and carrier proteins are involved. So these kind of proteins, there's special carrier proteins for active transport as well. So carrier proteins were involved in facilitated diffusion. You've also got carrier proteins involved in active transport. And they're very similar to these carrier proteins in the sense that in the molecule to be moved across the membrane, once again, it attaches to the carrier protein on the outside at a point. There's an attachment point, but like an active site. So the substance has to fit into this sort of like an active site, but you wouldn't call it an active site. The word active site is just for enzymes, but it's into a space that's like the active site. So the molecule fits in, and once it does fit in, then ATP is involved. ATP attaches to the carrier protein. And my way of thinking of it is that the carrier protein sort of flips around, a bit like a revolving door. And the molecule that's attached on the outside is now turned around so it's on the inside. So you imagine this, but these carrier proteins are a bit like a revolving door. So the molecule attaches on the outside. The ATP makes the carrier protein flip around, twist its shape, and all of a sudden the molecule's on the inside. So I've said the carrier protein binds to the molecule, and then using energy from ATP, the carrier protein changes shape or flips in such a way that it delivers the molecule inside. Once it's delivered the molecule inside, it flips back again and attaches to another molecule. Notice low to high concentration here against the concentration gradient, and notice very importantly, and I would highlight that in your notes, that process requires ATP. So ATP is needed. So I'm just highlighting it here just for your benefit. ATP is needed for this process. In other words, this is an energy requiring process. What we're kind of saying here is all the other processes could happen in a cell that wasn't really alive, even a cell that wasn't doing respiration, because respiration creates energy, creates ATP. So the other processes could have happened across membranes, even if they're not living cells. Whereas this process requires the cell to be very much alive and to be releasing a lot of energy. I've said here, once again, this is a specific process. When it means specific or selective process, the carrier protein must fit the molecule. If you approach the membrane and the carrier protein you can't fit, if you don't fit, then you can't be moved across. So for example, then if you have substances going into a cell by active transport, you should find that there'll be lots of carrier proteins for that substance. Membrane selective. As I've said here, a cell which needs to take in large amounts of a particular molecular ion will have large numbers of carrier proteins specific to that molecule, designed for or dedicated to that molecule. Active transport needs energy. It's supplied by ATP. The energy is supplied by ATP, and it's made in respiration in the cell's mitochondria. Now, here's something you're going to come across a lot in biology. If you look at a cell, if you're looking down the microscope at a cell, and you see that the cell has a lot of mitochondria, more than normal, then you're saying, oh, the cells must be doing more respiration than normal. In biology, that's usually an indication that the cell's doing a lot of active transport. Because cells that are doing a lot of active transport need a lot of ATP. And the only way they can get a lot of ATP is to do a lot of respiration. And a sign of that is that they've got a lot of mitochondria. So if a cell has a lot of mitochondria, in biology, you'll find this in A2. Every time you see cells with lots of mitochondria, you say, oh, I bet those cells are doing lots of active transport. You'll come across this in several topics. Also, other things that are associated with this then, if you supply more oxygen to a cell, why would a cell need oxygen? If a cell gets more oxygen, then it can do more respiration, and it can produce more ATP, and it can do active transport faster. So you'll discover this, that if a cell doesn't have oxygen, it can't make ATP, it can't release energy, and won't do much active transport. If you supply more oxygen to the cell, then it can do active transport faster. And you came across a wee, just have a check on time here. You came across a wee question at GCSE. There used to be a wee question where you had a beaker of water, or a beaker of, say, some sort of ions, and in the beaker you had a wee plant, and the roots of the plant, this is the wee plant, and the roots of the wee plant were dipping into the water, and they were taking up ions from the water, say nitrate ions. And they take up, as I said, it's root hair cells that are taking up the ions, and they're taking them up by active transport. And what you discovered was that if you bubbled oxygen into the water, through a wee pipe, you put oxygen into the water so the water contained more oxygen, you found that the root hair cells took up the ions faster by active transport. And the argument was you bubbled oxygen in here, bubbles of oxygen. You bubbled oxygen into the water, the root hair cells had more oxygen, and therefore they could do more active transport, and they could take up the nitrate ions quicker. So that was a wee GCSE thing. It doesn't usually come up at A2, but you might come across some. You also find there's another source of questions on this. You also find that if you add, say you were to add to the water a substance called cyanide, 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 and it's a chemical. And what it does is it stops respiration in cells. If you were to add some cyanide to this water, it stops respiration in the root hair cells, and it stops active transport. Because the cyanide stops respiration, therefore it stops the production of energy, and therefore the cells can't do active transport. So sometimes you'll come across questions like that. In fact, in my question booklet, and I won't have time today to look at many of the questions, I'll see when I get to the end of the notes here, just end of the theory stuff, how much time remains. I sort of want to limit myself to an hour here. I'll see how much time remains. I'll maybe have a look at a question. maybe when we're just doing it here, maybe we'll actually have a look at that question now. So the question I have in mind is question 9 in the question booklet there, and you'll see it's a question about this. And it's asking, suggest what happens to the uptake of sodium ions in red blood cells when red blood cells are treated with cyanide. And in the earlier part of the question, you figure that the sodium ions have been taken up by active transport. And if you add cyanide, then the red blood cells can't take up the ions by active transport. So you would say that active transport stops, the cyanide stops respiration in the cells, and so there's no energy available for active transport. There's no ATP available for active transport. So I'm going to come back to these questions too. But what I'm kind of saying here is that there's every kind of question in this question booklet, so you need this question booklet. So if you want to get the best benefit from this topic, get in touch with me by text. I'll send you all the stuff. Then you can sit and you can watch the video here, or you can Skype with me and we can talk about these things. We can go through the questions and everything. So that's the best approach. And the questions cover, these are all the most recent questions, and they cover all the areas you need to know about. So just going back then to going back to the active transport. That's the three topics, that's the three mechanisms then covered: diffusion, simple diffusion, facilitated diffusion, and active transport. Now, the best way to compare those, or to get a good quick comparison, is a table. And you'll see here, I've made a table that compares the three. Simple diffusion, facilitated diffusion, and active transport. On the top line on the table, I've said these three mechanisms, which of them are with the concentration gradient? In other words, which of them is from high to low concentration? And the answer is simple diffusion, high to low concentration; facilitated diffusion, high to low concentration; active transport, no, it's from low to high concentration, so it's against the concentration gradient. So that's the top line of the table. The second line of the table, and you need the notes here. There's no substitute really for having the notes. Energy required. Is energy required for simple diffusion? No. Energy required for facilitated diffusion? Nope. Yes for active transport. ATP is required. Types of membrane proteins involved. That's a difficult one. Well, there's no membrane proteins involved in simple diffusion. It's just movement of molecules through between the phospholipids, leaking through between the phospholipids, things like oxygen and carbon dioxide. Facilitated diffusion. Well, turns out there's two kinds of membrane proteins involved. If you remember, they were called channel proteins and carrier proteins. And then if we go to active transport, there's carrier proteins as well. So this table has come up, something similar to this. Just here, there's a question there somewhere along the lines of this. Let's see where it's at. Kind of a comparison question. Yep, question 4, part E, is kind of testing you on, do you recognize these different mechanisms? So 4, part E, if you've opened 4, part E, you'll see there the first thing: substances moved across the cell membrane against a concentration gradient. Active transport. Process by which substances are taken into the cell cause the cell membrane to enclose material in a vesicle. Oh, we haven't looked at that yet, but that's endocytosis. Movement of substance across the cell membrane from higher to lower concentration using protein carriers or carrier proteins, and that has to be facilitated diffusion. Moving across the cell membrane from high to low concentration without carrier proteins, simply through the phospholipid layers, that's simple diffusion. So that's that question. And then question 7, that is a question that's kind of based around this table that we're looking at in the notes. You need all this stuff. So next thing, a very important point in the table, element that I put into the table, I said, how is each process selective? In other words, how does each process select which molecules come through by that mechanism? So for example, simple diffusion, I've said only small or non-polar molecules can pass through by simple diffusion. So that's how it's selective. It decides that only small non-polar molecules through. Facilitated diffusion, how is it selective? Well, first of all, the channel proteins, they're molecule specific. You would say molecule specific because the molecule has to be the right shape to get through the channel. And secondly, the carrier proteins, they have to be, they're molecule specific as well, because if you don't fit into them, you can't get through. So that's the way in which that the facilitated diffusion is a specific process. And then active transport, exactly the same. The carrier proteins are specific for certain molecules. So if you approach the cell membrane as a substance and there's not a carrier protein that you can fit into, then you can't get across. Okay. Is the process stopped by cyanide? That was the poison that stops active transport. So the answer for diffusion, nope. Cyanide has no effect on simple diffusion or facilitated diffusion, but it stops active transport. Is the process faster with oxygen? Oxygen has no effect on simple diffusion or facilitated diffusion, but it does have an effect on active transport, because active transport requires the cell to be making energy in respiration, which requires oxygen. So more oxygen means more active transport. And the last point is just faster. Is the process faster with more membrane surface area? Is the process going to be quicker if there's more surface area on the membrane? And the answer is yes for all of them. Yes, yes, yes. Because if you have more membrane, simple diffusion, you've got more area to get across. Facilitated diffusion, you get more proteins and more channel proteins. The active transport, you have more of everything. So if the membrane's folded, it simply means the membrane's longer and more surface area. So all of them are speeded up by having more membrane. So you find this throughout biology that folded surfaces increase the surface area. Now, the last part of this video is about endocytosis and exocytosis, which comes under the heading of cytosis. Endocytosis and exocytosis. And these are methods for substances that are way too big. We're not talking about molecules and ions at this stage. We're talking about substances that are very big. In fact, we may be talking about large particles of material or food. The classic example of this was a GCSE. Do you remember that white blood cells called phagocytes? What did they do? They engulfed and digested bacteria. And essentially what was happening there was that the phagocyte, which was a white blood cell, was in very simple terms, it was eating the bacteria, but you wouldn't say that in an exam. If this was the white blood cell, usually they had an irregular shape like that. And this then was your bacteria. So that's your bacteria. Essentially what happened was that the white blood cell flowed around and kind of flowed around it. So it kind of flowed around the bacteria. And the word was, it engulfed the bacteria. So the bacteria sort of ended up inside this wee cap. And shortly after that, what happened was that this closed. So eventually the bacteria ended up inside the cell. Okay, so the bacteria is now inside the cell, inside like a wee pocket or a wee cavity. It's called a vesicle. Okay, so this was this was phagocytosis. You learned about this at GCSE. You said the white blood cell called the phagocyte engulfed the bacteria, and you referred to the process as phagocytosis. And what did it do with the bacteria once it had engulfed it? It digested it with enzymes. So effectively, it was eating the bacteria and breaking it down using enzymes. Now, that process of phagocytosis falls in this section. Phagocytosis is an example of endocytosis. Endocytosis means taking things in, cell taking in things, and they're big molecules. Like the bacteria is not it's big particles. The bacteria is not a molecule. Bacteria couldn't go in between the phospholipids or through a channel protein. It's way too big. So the cell's got another way of getting it inside, basically, and that is sort of just engulfing it in a so-called vesicle taken inside by phagocytosis. So these methods are for substances that are too big to pass through the phospholipid protein by diffusion, facilitated or active transport, facilitated diffusion or active transport. So this is usually for large food particles. And there's two types. Endocytosis is taking substances into the cell. Exocytosis is putting substances out. So if you want to put substances out, it's basically a reversal of this process. Say that's the substance you want to export out of the cell. Then what happens is that this vesicle containing the substance comes down to the cell membrane, and then it merges with the cell membrane again, basically. It merges with the cell membrane in such a way that now the substance then can be exported out of the cell, and that's exocytosis. So endocytosis is taking a substance in this way. Exocytosis is putting it out. Now, I've said, and sometimes you'll be asked to describe endocytosis, so you can see what you probably get 2 marks for it. So I've said the cell membrane. So if you're taking in a substance, you say the cell membrane invaginates or forms like a pocket. You could say forms and unfolds around the substance to be taken in. So it makes like a kind of a pocket, like a mouth almost. It takes the substance in. And then the second thing is the unfolded membrane then closes up to create a vesicle, which is creates a vesicle inside the cell. So that's the second. I've said the unfolded membrane creates a vesicle or a sac. You could say a sac. You call this thing a sac, S-A-C, S-A-C, which surrounds the substance. Now, endocytosis is also further complicated by two words. You have phagocytosis or pinocytosis. So endocytosis can be phagocytosis or pinocytosis. Phagocytosis is taking in something solid, like a bacteria. Pinocytosis is taking in a liquid. Not too important, but you would get a mark on an exam question if you knew the difference. So phagocytosis is a bit like this, the eating and drinking. Phagocytosis would be taking in something solid. Pinocytosis would be taking in something liquid. So phago and pinocytosis, and both those are examples then of endocytosis. Exocytosis, as I said, then is putting something out of the cell, and you'll see quite a nice diagram there which shows how the cell might produce something that it might send out of the cell by exocytosis. An example of that would be cells are always making things that they're exporting. So, for example, cells that line the inside of your stomach, for example, are making enzymes to digest your food, and they're making those enzymes and then they're exporting them out of the cell into the cavity of your stomach to digest your food. That's an example of exocytosis. Other examples, if you think about the stuff inside your mouth, saliva, where does it come from? It's made by the cells that line your mouth and your nose and that. And so those cells are making this, let's call it mucus, saliva, mucus. It's made by the cells that line your mouth. And then those cells secrete it. The word secrete is used a lot instead of export. Secrete means to produce something to put out of the cell. So you could say a cell secreted some enzymes. It means it makes some enzymes and then it puts them out of the cell by exocytosis. Okay, so that diagram at the bottom of the page there shows exocytosis and endocytosis. Now, can I say to you that it's all about the questions? Okay, it's good enough kind of trying to understand the stuff just from the video or reading the notes or whatever. But at the end of the day, it's doing the questions. And this is a difficult topic. Teachers don't find it easy. All those differences between simple diffusion, facilitated diffusion, active transport, they're quite awkward. And sometimes different textbooks will say different things. And teachers are never quite certain what the examiner wants. One of the best guides, however, is to look at a past paper question. So in the past, in fact, in this question booklet here, I have a question and questions about this. So, for example, a question on this topic, this lends itself to all sorts of questions, but it lends itself to an essay question. A recent essay question was compare the processes of simple diffusion, facilitated diffusion, and active transport. Compare them, giving similarities and differences, sort of thing, and also saying how each is selective. So that selective bit's important. So you're saying how does each process only sort of fit one particular kind of molecule, and doesn't fit another. Is selective in determining what gets across them. This is quite hard, but doing that essay and the answer scheme will help you a lot. So I'm looking at the question. It was question 12. I think the first part of I maybe don't have the original question here, but the first part of it was basically asking you to compare simple diffusion, facilitated diffusion, and active transport. And then the second part was asking you about the selectivity of it. And there was 13 marks in one essay. So useful to look at that. There's good questions there about the cyanide thing too. Question 11 is about the cyanide. Very good question. Actually an English board question, but it's a very nice question and it tests you well to understand that. Other questions on this, question 3 then, is showing you a big picture of the cell membrane. Doing questions often introduces you to great diagrams, nice clean diagrams, and you can see exactly what's happening there. It shows you a channel protein on that one. And question 3 continues about cell membranes as well, and then question 4 and so on and so forth. Anyway, if this is helpful to you, you need to have my booklets and stuff. There's a booklet here. And this booklet of short questions has got some. There's some 67 questions on this topic. So that's me kind of interrogating you, asking you a lot of questions about this topic, and you've got the answers. So you can sit quietly and go through it and say, could I answer all those questions? If you can answer all those questions, then you've kind of got this topic, okay. And at the end of the day, you shouldn't be just reading the notes and understanding the notes and thinking, that's it, I can't understand this. You must do the questions. And if you can answer all the questions that you get, then you have a good enough understanding. You don't have to get into the minute understanding of all the different processes. Answer the questions, that's good enough. Look at the answer scheme. Look at the answer scheme there for that question 12. Look at the answers they give you when they ask you to compare simple diffusion, facilitated diffusion, and active transport. You've got the answer scheme there. You can see what you do need. Okay, so there you are. As I say, there's another video on the osmosis half of this topic, and you can get access to it as well. just text me, and I'll get all the stuff to you. And if you want, then we can Skype, and we can Skype through the Skype is most useful for going through the questions. So if you have the questions done, you see if I send you the questions, and you have the answers with them. But if you're good in discipline, you can try and do the questions. See if you can do them. Any question you have difficulty with, as soon as we're on the Skype, you can say, question 9, I see your answers for that, but I don't know where the answers come from or don't understand. Can you explain that? And I'll sort that out for you. Okay, good. So, well done. Thank you very much. And I'll be doing videos on all the topics, all the AS topics. So you probably already have done molecules and cell infrastructure, cell ultrastructures it's called, and so on and so forth. So I hadn't realised, I thought when I started doing these videos that they normally would, an hour would be enough to cover each topic. Like there would cover cell physiology. Well, I've actually discovered it took an hour to do the water potential part of it, first of all, and then I've spent another hour here doing this part of it, so I think it took 2 hours, so it's quite a lot of stuff involved. So okay. All the best. Bye.